Hello everyone, anyone who's watching this. My name is Umandeep Singh and my roll number is 68. I currently study in chemical engineering in NIT Jalandhar. And today I'm going to be presenting this presentation, that is assignment 1 of heat treatment, and my topic is heat transfer correlations in pool boiling. This assignment is to be submitted to Dr. Shashikant Yadav, and this is my presentation on the topic heat transfer correlations in pool boiling. And without any ado, I would like to begin. First of all, we have the table of contents. The purpose of this has been just to make the presentation a bit organized and not be disorganized, and that it can be accessible easily to anyone who may want to watch a specific topic. They can just see their number here and move on to them. So I would like to give you a brief overview of all that has been covered in this presentation and then move on. So at number 1, we have what is heat transfer. The purpose of having this here is that we really need to learn about heat transfer because our topic is heat transfer correlations in pool boiling. If we don't know what is heat transfer, how are we even going to understand the transfer correlations in pool boiling? Interesting, isn't it? So first of all, as I said, we have what is heat transfer. Then we will have history and terminology of heat transfer. We will have all the theories that were published and rejected and improved upon regarding heat transfer, because to learn about our present and our future, learning the past is very, very important. And then after that, we will learn about the methods of heat transfer. This is done because all three methods at some point are being utilized in pool boiling. The pan heats up via conduction, natural convective boiling takes place, and after maximum critical heat flux has been achieved and we move on to film boiling, after reaching the latent frost point, radiation comes into play. So therefore, we will learn about all the three major methods of heat transfer, that are conduction, radiation, and convection. Types of convection. Convection has been studied in detail because it is mainly convection which is in play in this whole boiling ordeal. And Newton's law of cooling is mainly applicable to convective heat transfer. So we'll be studying that in detail too. That was given us by Lord Isaac Newton, which is a very, very important part of this presentation and boiling as a whole. And as boiling is sort of a phase change, that is change of one state into other, change of water into vapor, or any solid or any liquid into its gaseous state, we'll be studying about phase change. And we also need to know the difference between boiling and evaporation, so we'll be studying the vaporization part. That is what boiling constitutes of in detail. Therefore, we will have types of boiling and types of pool boiling as well. A little minor parts have been skipped in this. They will just be roughly skimmed over in the presentation. After that, we have to study the pool boiling curve, which has all the important points O, A, B, C, D, E, which is moving from natural convective boiling to nucleate boiling to transition boiling to film boiling. And it is very, very important to study the regimes and the pool boiling curve side by side as they all go together. They'll help us in understanding boiling even better, and the pool boiling curve will also have the important points, that is the critical heat flux point and the minimal heat flux point, also known as the latent frost point. After that, we will have a brief study of the regimes in tabular form, where I'll be listing their important points and how they operate, how they work, and what are they about. And after studying the regimes, we will have a few minor applications of boilings in chemical engineering and in our day-to-day life. And then we have our heat correlations. First of all, we will have the Rosnow equation, which was given to us by Rosnow. Then we will have minimum and maximum heat flux, and also film boiling correlation. So this is what our table of contents in this presentation is. We will start from a basic thing as basic as heat transfer and move up slowly by slowly, step by step, to heat transfer correlations. Moving on. So, first of all, we have a very basic question. What is heat transfer? what is this subject we are studying? What is this chapter we are studying? So, in general, heat transfer describes the flow of heat, thermal energy due to temperature differences and subsequent temperature distribution and changes. The study of transport phenomena concerns the exchange of momentum, energy, and mass in form of conduction, convection, and radiation. These processes can be described via mathematical formulas. So basically it has given us a brief idea of what heat transfer is, how heat flows. It incorporates various processes such as conduction, convection, and radiation, and these processes are governed and things about them can be calculated through some several formulas. Now one might ask, how can we arrive at these several formulas? Here we have the fundamentals of these formulas are found in laws of conservation of momentum, energy, and mass in combination with constitutive laws, relations that describe not only the conservation but also the flux of quantities involved in these phenomena. So all in all, this is what constitutes heat transfer. Transfer of heat governed by temperature differences, its types, and their formulas, which have been obtained by further basic formulas. Moving on, we have history and terminology. So the basic saying goes, without studying our past, we can't really understand the present and the future, which is very right. So we'll be delving into the past and learning about the basics about heat transfer. Here we have, without external help, heat will always flow from hot objects to the cold ones, which is a direct consequence of second law of thermodynamics. We call that heat flow. In the early 19th century, scientists believed that all bodies contained an invisible fluid called caloric, a massless fluid thought to flow from hot to cold objects. Caloric was assigned properties, some of which proved to be inconsistent with nature. For instance, it had weight and it could not be created nor be destroyed. But its more important feature was that it was able to flow from hot bodies to cold ones. There was a very useful way to think about the heat. So this was our first theory, that is calorics. Now moving on. History and terminology part B. Thomson having a pretty feisty moustache in the top right and Joule having a very feisty beard in the bottom right showed that this theory of caloric was wrong. Heat is not a substance as supposed, but a motion at a molecular level, so-called kinetic energy. A good example is rubbing our hands against each other. Both hands get warmer even though initially they were at same cooler temperatures. Now, if the cause of heat was a fluid, then it would have flowed from a hotter body with more energy to another with less energy, that is colder. So basically, according to second law of thermodynamics, hotter to colder. Instead, hands are heated because kinetic energy of motion, rubbing, has been converted to heat in a process called friction. The flow of heat is happening all the time from any physical entity to the object surrounding it. The only domain free from heat flow would have to be isothermal, that is, the temperature remains constant. As there is no temperature difference, heat won't travel, and completely isolated from any other system allowing such heat transfer. Such a system is practically impossible to create, and that is completely true that this can only happen in somewhat a hypothetical situation, as we can't really make the temperature constant over a large body or any body of considerable size visible to a naked eye, and to keep it completely isolated is another impossibility, so I completely agree with the statement. Moving on, we have methods of heat transfer. There are three methods of heat transfer mainly, namely they are conduction, convection, and radiation. Now, here is a beautiful example to our right, and if we look at it, we can see all the three heat transfers in it. So first of all, the fire provides and heats up the bottom of the pan, but how does the top of the pan feels hot? See, and even the handle. The molecules stay in their position and vibrate when they gain kinetic energy and become excited. They provide this to the neighboring molecules and collide with them by staying in their own position by vibrational energy and heat them up as well. This cycle continues till the whole of the pan has been heated. So this is how conduction heating takes place. Next is convection, and in this particular case we will have natural convection. So one might ask, how does it take place? So in this case, convection will happen as the bottom of the pan will get heated. It will heat up the bottom water molecules, and as they will get heated, they will expand and get excited, and hot things generally rise. Also, they will experience a buoyant force due to decrease in density, and they will rise up. And cold things, that is cold water, will come to take its place, which will also heat up, and therefore a convection current would be formed. Radiation is quite probably the most interesting of the three. One might think, how does it take place? And it is actually a very uncommon and very interesting phenomena. It takes place without even a medium. You don't even need to touch things to feel the heat. Like, our hand will still feel hot even if it's not touching the pot and is just near the flame. Radiation is a method of heat transfer that does not require any medium. I'll be explaining them in a bit more detail here. Conduction is defined as the process in which heat flows from objects with higher temperature to the objects with lower temperature. An area of higher kinetic energy transfers thermal energy towards the lower kinetic energy area. High-speed particles clash with particles moving at a slow speed. As a result, slow-speed particles increase their kinetic energy. This is a typical form of heat transfer and takes place through physical contact. Conduction is also known as thermal conduction or heat conduction. The rate of conduction can be calculated by the following equation. Q, that is heat transfer, is equal to Ka delta T by D. And K is the coefficient of heat transfer, A is area of cross section, D is length of body, and T hot minus T cold is basically delta T, that is difference in temperature of two things through which heat has to travel. Here we have, as I said, Q is the transfer of heat per unit time, K is thermal conductivity of the body, A is area of heat transfer, T hot is the temperature of the hot region, and T cold is the temperature of the cold region. D is the thickness of the body. Following are the examples of conduction. Ironing of clothes is an example of conduction where heat is conducted from iron to the clothes. Heat is transferred from hands to ice cube, resulting in melting of ice cube when held in hands. Heat conduction through the sand at beaches. This can be experienced during summer. Sand is a good conductor of heat. So basically we have conduction, its heat transfer equation, and some examples of conduction here. This has been conduction in a brief summary. Now moving on, we will study radiation before convection because we will be studying convection afterwards in a bit detail, as boiling mainly incorporates convection. Moving on, we have radiation. As first of all, we can see in that cute little diagram on the top, we are feeling the heat without even touching the fire. Radiation actually does not need a medium. So the heat transfer mechanism in which no medium is required is called radiation. It refers to the movement of heat in waves, as it does not need molecules to travel through. The object need not be in direct contact with another to transmit heat. Whenever you feel heat without actually touching the object, it is because of radiation. Moreover, color, surface orientation, etc. are some of the surface properties on which radiation depends greatly. In this process, energy is transmitted through electromagnetic waves called as radiant energy. Hot objects generally emit thermal energy to cooler surroundings. Radiant energy is capable of traveling in vacuum from its source to the cooler surroundings. The best example of radiation is solar energy that we get from the sun, even though it is miles away from us. Approximately 360,000 kilometers of vacuum between us, and still we are able to get the warmth of the sun due to which life survives on Earth. That is not just that. Nuclear radiation has been used as various sorts of power fuels and all. Radiation is is a technology of the future really. Radiation is what's gonna unlock the key to the future, and it is a great phenomena. Moving on, we have a brief explanation on radiation. As temperature rises, the wavelengths in the spectra of radiation emitted decreases and shorter wavelength radiations are emitted. Thermal radiation can be calculated by Stephen Boltzmann law. P is equal to E sigma A Tr minus Tc raised to power 4, where sigma is Stephen's constant, A is area of where A is area of cross section and E is emissivity. Following are the examples of radiation. Microwave radiation emitted in the oven is an example of radiation. UV rays coming from the sun is an example of radiation. The release of alpha particles during the decaying of uranium-238 into thorium-234 is an example of radiation. Now moving on, we have the man of the hour, cometh the man, cometh the hour, convection. In science, convection implies the form of heat transfer by real movement of matter. In conduction, the particles weren't really moving, but here they are. So it only occurs in fluids. Fluid alludes to any substance whose molecules move freely from one place to another, such as liquid and gases. It happens naturally or even forcefully. Gravity has a great role to play in natural convection, such that when the substance is heated from below, leads to expansion of the hotter part. Due to buoyancy, the hotter substance rises as it is less dense, and the colder substance replaces it by sinking at the bottom due to high density, which then gets hot, moves upward, and process continues. In convection, on heating up the substance, its molecules disperse and move apart. When the convection is performed forcefully, the substance is compelled to move upwards by any physical means such as the pump, example air heating system. So here we have briefly studied about types of convection, that is free and forced, and how convection actually involves particles moving instead of conduction. Moving on, we have types of convection. Two types of convective heat transfer may be distinguished. Free or natural convection. When fluid motion is caused by buoyancy forces that result from density variations due to variations of thermal temperature in the fluid. In the absence of an internal source, when fluid is in contact with a hot surface, its molecules separate and scatter, causing the fluid to be less dense. As a consequence, the fluid is displaced while the cooler fluid gets denser and the fluid sinks. Thus, the hotter volume transfer heat goes towards the cooler volume of that fluid. Familiar examples are the upward flow of air due to a fire or hot object and circulation of water in a pot that is heated from below. Forced convection. When a fluid is forced to flow over the surface by an external source such as fans, by stirring and pumps, creating an artificially induced convection current. So free or natural convection happens on its own without any external sources, and in forced convection, external sources are primarily responsible for causing heat transfer. Moving on, we have Newton's law of cooling. Isaac Newton considered the convective process and suggested a simple formula for the cooling. Delta temperature body, that is temperature change in body, divided by delta time is directly proportional to temperature of body minus temperature infinity, where T infinity is the temperature of the oncoming fluid. This expression proposes that energy is flowing away from the body on itself, and the steady state form of Newton's law of cooling defining free convection is described by the following formula. Q, that is heat, is equal to H into T body minus T infinity, where H is the heat transfer coefficient. The coefficient can be denoted with a bar like shown here, H bar, which indicates an average over the surface of the body. H without a bar denotes local values of the coefficient. So if it's a large body, H without the bar may denote its value at some particular point, where H bar indicates the average value of the whole bulk body. Moving on, we have effects of heat transfer. The basic effect of heat transfer is that the particles of one substance collide with the particles of another substance. The more energetic substance will typically lose internal energy, that is, cool down, while the less energetic substance will gain internal energy, that is, heat up. The most blatant effect of this in our day-to-day life is a phase transition. Yes, ladies and gentlemen, this is why I have been nagging you up to this point. As boiling is a phase transition itself, this is why it is important to study. A phase transition where a substance changes from one state of matter to another, such as ice melting from a solid to a liquid as it absorbs heat. The water contains more internal energy, that is, the water molecules are moving around faster than in ice. In addition, many substances go through either thermal expansion or thermal contraction as they gain and lose energy. Water and other liquids often expand as it freezes, which anyone who has put a drink with a cap in the freezer for too long has discovered. So basically it shows that water, when frozen, expands a bit. It is known that if you completely fill a bottle it up and keep it in the fridge, either the bottle will explode a bit or the cap will come off. That is because it has already been filled and water still expands, so there is no more space. So it has to either open up or burst. Moving on from here, we have phase change. So studying up a little in detail about the phase change, a phase change is when matter changes from one state to another, mainly solid, liquid and gas. We won't be considering plasma in this case. These changes occur when sufficient energy is supplied to the system or a sufficient amount is lost, and also occur when the pressure on the system is changed. The temperatures and pressures under which these changes happen differ depending on the chemical and physical properties of the system. The energy associated with these transitions is called latent heat. We will study about all these in a little while, but on the right side for now we have a brief diagram showing us the basic 6 transitions between gas, liquid and solid. We will study them in a little bit more detail in the next slide. So first of all, we have vaporization. Vaporization of an element or compound is a phase transition from liquid phase to vapor. There are two types of vaporization: evaporation and boiling. So in the first image we have a tea or a warm water giving out vapors and it is getting vaporized. Condensation. Condensation is the change of physical state of matter from gas phase to liquid phase and is the reverse of vaporization. The best example of condensation, as shown in the figure, is rain. Rain falling is basically conversion of vapor into liquid. Melting or fusion is a physical process that results in phase transition of a substance from solid to a liquid. A good example would be an ice cream melting as ice changes to water and solid to liquid, or milk or frozen milk to liquid milk. Moving on, we have solidification, also known as freezing, is a phase change of matter that results in product of solid. As shown in the figure, water turns into ice, it's cold, blah blah blah. And then we have sublimation. Sublimation is the transition of a substance directly from solid to the gas state without passing through the liquid state. If we see on the right, we see dry ice sublimating from solid to gaseous. Deposition. Deposition is the phase transition in which gas transforms into the solid without passing through the liquid phase. Moving on. Here we have a phase change diagram. In this diagram, we see it is a very basic phase change diagram. They can be very extensive in nature. Here we have, first of all, as we can see, we have temperature on the y-axis and heat on the x-axis. As the substance is first a solid, it's heated and the temperature rises linearly, but then it suddenly stops. It melts into the liquid, but even during its melting, the temperature doesn't rise until whole of it has melted and is a liquid. And then the temperature rises again till the same phenomena occurs. The temperature stops rising, The vaporization occurs and the temperature doesn't rise again till vaporization is complete. So this is due to the fact that all of the heat energy is being used to break the bonds and the cohesive bonds between these particles instead of going into rising the temperature. Then the heat involved is latent heat. Latent heat is defined as the heat or the energy that is absorbed or released during phase change of a substance. It could either be from a gas to a liquid or liquid to a solid and vice versa. The latent heat is related to a heat property called enthalpy. However, an important point that we should consider regarding latent heat is that the temperature of the substance remains constant. We deal with two types of latent heat: latent heat of fusion and latent heat of vaporization. Vaporization. Conversion of a substance from liquid or solid phase into gaseous vapor phase if conditions allow the formation of vapor bubbles within a solid liquid. The vaporization process is called boiling. Direct conversion from solid to vapor is called sublimation. Heat must be applied to a solid or liquid to effect vaporization. If the surroundings do not supply enough heat, it may come from system itself as a reduction in temperature. The atoms or molecules of a liquid or solid are held together by cohesive forces, and these forces may overcome in separating the atoms or molecules to form the vapor. The heat of vaporization is a direct measure of these cohesive forces. Moving on, we have evaporation. Evaporation, the process by which an element or compound transitions from its liquid state to its gaseous state below the temperature at which it boils. In particular, the process by which the water enters the atmosphere as vapor part of vapor. Evaporation, mostly from the sea and from vegetation, replenishes the humidity of the air. It is an important part of the exchange of energy in earthly atmosphere system that produces atmospheric motion and therefore weather and climate. The rate of evaporation on the temperature difference between the evaporation surface and the air, the relative humidity and the wind. Finally, we move on to boiling. Boiling is the rapid vaporization of a liquid which occurs when liquid is heated to its boiling point. The temperature at which vapor pressure of the liquid is equal to the pressure exerted on the liquid by surrounding atmosphere. There are two main types of boiling: nuclear boiling, where small bubbles of vapor form at discrete points, and critical heat flux boiling, where the boiling surface is heated above a critical certain temperature and a film of vapor forms on the surface. Transition boiling is an intermediate, unstable form of boiling with elements of both types. The boiling of point of water is 100 degrees Celsius or 212 degrees Fahrenheit, but is lower with decreased atmospheric pressure found in higher altitudes. Difference between evaporation and boiling. Evaporation is a normal process that occurs when liquid form changes into gaseous form while causing an increase in pressure or temperature. Evaporation usually occurs on the surface of the liquid being heated up, whereas boiling is an unnatural process where the liquid gets heated up and vaporized due to continuous heating of liquid, and also boiling usually occurs on the entire mass of the liquid that gets heated up. Basically, evaporation is a surface phenomenon and boiling is a bulk phenomenon. Bubbling effect is not visible in evaporation, but bubbling effect is clearly visible in the process of boiling. As it is a surface phenomenon in evaporation, boiling clearly isn't visible, but in the bulk phenomena boiling, we can clearly see small bubbles rising up from bottom to the top. The process of evaporation is usually slower and more carried out when compared to boiling. But in boiling, the process of boiling is much quicker and the process happens quite rapidly as well. So now we will continue with types of boiling. First of all, we have pool boiling. It refers to the condition in which hot surface is somewhat below the free surface of a stagnant liquid. The hot surface is actually submerged inside a liquid, and its motion near the surface is due to a free convection only. Then we have Forced convection boiling. In pool boiling, it is free convection as convection currents are set up freely due to density and buoyancy as explained earlier, but in here it is forced convection. That is, it is not natural and heat transfer is caused by external sources. In this case, fluid motion is provided by external means like a pump as in case of modern boilers. The forced convection improves the rate of heat transfer due to increased heat transfer coefficient. As external sources as well as internal sources in some cases are working hard to provide with the boiling and the heat transfer, it is generally more fast and intense than the earlier one. Then we move on into subcooled or local boiling. Subcooled or local boiling is the case of pool boiling, that is, when the material is submerged inside a liquid and and the convection is natural below its saturation temperature. In such a case, bubbles formed at the heated surface are condensed in the liquid as they leave the surface. Saturated boiling or bulk boiling. This is also the case of pool boiling in which liquid is at its saturation temperature. This is similar to the subcooled or local boiling, just that in its saturation temperature has been received. So now we move on to the main event, the pool boiling curve. So first of all, we have natural convection boiling. In it, bubbles really haven't been formed and boiling is going on its own and it slowly rises. This OA part is natural convection boiling. In it, the temperature range is, the bottom range is 103 degrees Celsius and the surface temperature is 100 degrees Celsius. Boiling has just been achieved and it is going on at a normal rate, we can say. Then bubbling starts to form. Here it is AB point. It is nucleate boiling. AB, in it the bottom surface gets more heated up and the bubbles slowly start to rise. In B2C, the bubbles rise up higher and higher as heat transfer is maximum. This is when maximum critical heat flux has been obtained. The reason it decreases after this is because the bubbles start merging together. They merge together, grow in size and sink to the bottom. On sinking to the bottom, they form a thin film. At this thin film, then earlier, because bubbles were rising up, maximum heat transfer was occurring. This thin film acts as a resistance to boiling. So as it acts as a resistance to boiling, Q boiling, that is measured in watt per meter square, starts to decrease till it reaches a minimum point D, also known as the Leidenfrost point, which is the minimum critical heat flux. Now one may ask, like as this graph is showing, at first from O to A it increases, at boiling has just started and A to B bubbles start, B to C bubbles start and going up at an increased rate, and C to D the film forms which acts as a thermal resistance. Then the graph should keep on going down. One may ask, why does it go up from D to E? This is actually a very good question and there is a very interesting reason behind it. One may wonder, what is this reason? Now, if we pay a little attention and use our brain, we can figure it out that it is using radiation now. Yes, that is correct. Instead of conduction or convection, radiation is taking place. This was the point of studying all the conduction, convection and radiation, so we could understand this in detail. Radiation takes place and it involves way more heat than conduction or convection, so it rises upwards and upwards and upwards. So from D to it also rises. So again, a quick summary. From O to A, it is natural convection boiling. Natural convection currents have been set up and boiling takes place and water gets converted to steam or any liquid into its vapor. Then A to B, bubbles start forming and rising up, and B to C, they rise up at a higher rate, leading to maximum heat transfer. Then these bubbles collide with each other, grow in size, also submerge and merge together to form a film at the bottom, called as which acts as a thermal resistance. This is called transition boiling, and a minimum amount of flux is achieved, which is the latent first point. After that, the minimum has been achieved. The boiling starts incorporating radiation into it. That is the reason of E being so high. Moving on from the pool boiling curve, these all four stages, that is natural convection boiling, nucleate boiling, transition boiling, and film boiling, are regimes of pool boiling. We are going to look at them in a little bit more detail from now on. Various regimes of pool boiling. Free convection boiling. In this regime, the excess temperature TE is very small. The heat is transferred from wall to the liquid. Density of liquid at its surface decreases. The hot liquid moves up and cold liquid descends and sets up free or natural convection currents. Thus, heating in this case is by natural convection. As explained earlier, this is the case here, and we can see it in the diagram to the right. In this case, vapor is produced at free surface of a liquid by evaporation. Hence, this regime is known as interface evaporation. Nucleate boiling. Heat flux increases rapidly with increase in excess temperature. The value of excess temperature is in the range of 5 degrees Celsius to 30 degrees Celsius. In this regime, the bubbles start forming at certain location on the heated surface. It represents the start of boiling process. During period A to B is called the regime of pool boiling. The bubble formed are very few in number. These bubbles condense in the liquid and do not reach up to the free surface of the liquid. This regime is referred as an isolated nucleate boiling or unstable boiling. With the further increase in acceptance temperature, excess temperature, the large number of bubbles are formed on almost all of the surface. These bubbles grow in size and rise to the free surface of the liquid and form slugs of vapor which leave the surface. Transition boiling. With the increase in the temperature difference, bubble formation is very high. These bubbles start to combine and form a blanket vapor on the heating system. In this regime, the vapor film is not stable and collapses. Due to this, a part of the surface will have film boiling and the remainder surface will have nuclear boiling. This is sort of a mixture between the two. For this reason, the regime is called unstable film boiling as well. After that, we have stable film boiling. Please note the part in transition boiling. It is called transition because it is a transition between film boiling and nucleate boiling. A part of the surface undergoes film boiling and the remainder goes nucleate boiling. After that, we move on to the stable film boiling. Thus, the region beyond DI up to the film is stable on the surface, and this region is called the regime of stable film boiling. Applications of boiling. Household refrigerator, which is refrigerant boiling, steam power plants boilers, chemical industries boilers, cooling of nuclear reactor by coolant boiling, industrial kettles, that is electric component cooling by boiling of liquid in which these are placed, regenerative cooling of rocket motors. Now, these are all in regards to the chemical engineering and technical aspects. Let me just provide you for fun some household advantages and applications of boiling. Boiling can be used to make water potable, that is purify it. It is also used in cooking, and another use of it can be purification and all, which definitely kills all the germs. Moving on, we have heat transfer correlations. So we will be studying heat transfer correlations for each aspect of boiling and all the regimes which we have just studied. First of all, we have heat transfer correlations in pool boiling. Boiling regimes differ considerably in their character as we have just studied. Different heat transfer relations need to be used for different boiling regimes. As we have already studied, all of the four main boiling regimes are so different from each other. We need different heat transfer regimes for each of them. In the natural convection boiling regime, heat transfer rates can be accurately determined using natural convection relations. As said, there is nothing abnormal in it, no bubbles are formed, there is no fluctuation in the heat flux, so we can calculate them easily. Now, when we come to nucleate boiling, no general theoretical reactions for the heat transfer in the nucleate boiling regime is available. Experimental based correlations are used. The rate of heat transfer strongly depends on the nature of nucleation and the type and the condition of the heated surface. As we see the graph, the natural convection relations there in the natural convection boiling, and in the nucleate boiling relations we just have experimental correlations. This graph is used to show different relations are used to determine the heat flux in different boiling regimes. Moving on. For nucleate boiling, a widely used correlation proposed in 1952 by Rosnow, which is also known as the Rosnow equation, is given as nucleate boiling heat flux is viscosity of the liquid into enthalpy of vaporization multiplied by gravitational acceleration into density of liquid minus density of vapor divided by surface tension of liquid vapor interface raised to power half into specific heat of liquid into the difference of surface temperature of heater and fluid divided by experimental constant that depends on the surface fluid combination divided by Prandtl number of the liquid raised to power experimental constant that depends on the fluid whole raised to power thrice. Now this is the equation where various terms are given below. I'll be going over them briefly. Q nucleate is the nucleate boiling heat flux, mu1 is viscosity of the liquid, HFG is the enthalpy of vaporization, G is gravitational acceleration, rho L is density of liquid, rho V is density of vapor, sigma is the surface tension of liquid vapor interface, CPL is the specific heat of liquid, that is in joule per kg, Ts is surface temperature of heater, T saturation is saturation temperature of the fluid, CSF is the experimental constant that depends on the surface fluid combination. Prandtl number of the liquid is PRL and N is the experimental constant that depends on the fluid. Heat transfer correlations in nucleate boiling. The values in Rosnow equation can be used for any geometry since it is found that rate of heat transfer during nucleate boiling is essentially dependent on geometry and orientation of the heated surface. The correlation is applicable to clean and relatively smooth surfaces. Error for heat transfer rate for a given excess temperature is 100%. Error for the excess temperature for a given heat transfer rate for the heat transfer rate and by 30%. Critical heat flux. The maximum or critical heat flux CHF in nucleate pool boiling is given as Qmax is equal to CCR into CHF into HFG into sigma G rho V square into rho L minus rho V raised to power 1 by 4. CCR is a constant whose value depends on the heat geometry but generally is about 0.15. The critical heat flux is independent of the fluid heating surface combination as well as viscosity, thermal conductivity and specific heat of the liquid. The CHF increases with the pressure up to about 1/3 of critical pressure and then starts to decrease and becomes 0 at critical pressure. The CHF is proportional to enthalpy of HFG and large maximum heat fluxes can be obtained using fluids with the large enthalpy of vaporization such as water. The critical heat flux is proportional to enthalpy of vaporization and large maximum heat fluxes can be obtained using fluids with a large enthalpy of vaporization such as water. Here we have values of coefficient CCR, that is a constant whose value depends on heating geometry in this table for various shapes and sizes. Moving on, we have minimum heat flux. The minimum heat flux point in the boiling curve is the boundary between the transition boiling regime and the film boiling regime. The minimum heat flux Q minimum is reached when the heat flux is equal to the minimum vapor formation rate that can sustain a stable vapor film over the heating surface. In the controlled heat flux boiling, nucleate boiling is established and then the heat flux falls below the minimum heat flux point. The minimum heat flux is referred to as the Leidenfrost point. Here we can see the Leidenfrost point in this graph marked with the blue circle dotted up. Q minimum is equal to 0.09 rho V HLV into G sigma rho L minus rho V divided by rho L plus rho V whole square raised to power 1 by 4. Then we have film boiling. The heat flux for film boiling on horizontal cylinder or sphere of diameter d is given by this equation, where Q film is equal to C film into G kV cube rho V rho I minus rho V HFG plus 0.4 C PV Ts minus T saturation divided by mu V into D into Ts minus T saturation raised to power 1 by 4 into Ts minus T saturation. C film is equal to 0.62 for horizontal cylinders and 0.67 for spheres. At high surface temperatures, typically above 300 degrees Celsius, the heat transfer across vapor film by radiation becomes significant and needs to be considered. This is the reason of the sudden upward growth of the graph. And Q radiation is equal to E sigma Ts raised to power 4 minus T saturation raised to power 4, where sigma is Stephen's constant. Q total is equal to Q film plus 3 by 4 Q radiation. It should be noted that Q radiation is still less than Q film. And now I would like to conclude this experiment and this presentation. Here are some of the resources I used for making this video and this presentation. Thank you. It has been a great journey explaining this to everyone. I would like to thank my teacher for giving me this opportunity, as well as my friends who have educated me on various topics and guided me how to record this video as well as perform this PPT. I'm very thankful, and I would like to conclude this here. Thank you.